Assalamualaikum warahmatullahi wabarakatuh. We are from Group 7 and our title is CFD Analysis Airflow and Ventilation Efficiency in an Enclosed Parking Lot. In this project, we are leveraging virtual simulation to analyze the complex airflow and temperature distribution within enclosed parking lot. This computational approach is highly crucial in modern engineering because it allows us to visualize flow features that are otherwise invisible and thus multiply design iteration efficiency without the high cost and time required to build physical prototypes. For the problem statement, enclosed parking lots in tropical climates like Malaysia suffer from heat accumulation and toxic gas build up like carbon dioxide and nitrogen dioxide due to poor natural airflow and inefficient ventilation system. Our main objective is to simulate airflow and temperature distribution within an enclosed parking structure using CFD software. Number two, to evaluate how different ventilation configuration affect airflow efficiency and thermal comfort for users.
For the methodology part, to create the geometry for our analysis, we use Autodesk Inventor to build a 3D model of the enclosed parking lot. Instead of simplifying the room, we specifically include the structural pillars, ceiling beam, and vehicle blocks. This ensures our simulation accurately capture real-world airflow, obstruction, and blockage ratio. Next, we import the model into ANSYS for meshing, which splits the air volume into a grid of small cells for the software to calculate. As you can see, I made the grid much smaller and tighter around the inlets, outlet, and pillars. This gives us high accuracy where the air moves fast while saving computer processing time in the empty areas. Finally, I set up the boundaries and physics in ANSYS Flint. The fresh air fans are set as velocity inlets based on the ventilation standard. The exhaust vents are pressure outlets, and the walls, pillar, ceiling, floor, and car are set as no slip boundary condition. This completes the setup, making it ready for the simulation.
Moving on the visual analysis phase. Three main graphical output were extracted from the ANSYS Fluent software to evaluate the ventilation efficiency within this enclosed parking structure. First, looking at the velocity vector, this output is utilized to visualize fluid flow behavior in details. Through these vector plots, we can clearly identify the formation of wet regions, which are low velocity drop zones, as well as stagnant air pocket occurring immediately behind the vehicle structure. Next, for the temperature contours, mapping the thermal distribution is crucial to observe heat dissipation across the fluid domain and to detect a critical hot spot tapping around the car surface. Finally, residual plots are directly monitored during the solving process to assess a solver convergence, thereby verifying the mathematical and numerical stability of our computational model.
Next, we move to the analysis and comparison the effect of inlet velocity on airflow distribution. This slide shows the effect of inlet velocity on airflow behavior. As the inlet velocity increased from 1 to 4 meter per second, the average velocity increased from 2.46 meter per second to 5.45 meter per second, showing stronger airflow through the domain. The velocity contours show that higher velocity creates stronger acceleration zones and more directional flow paths. However, excessive velocity also creates more localized jets and uneven distribution. Therefore, case A at 2 meter per second provides a more balanced airflow pattern. Next, we move to the airflow efficiency and flow resistance. For airflow efficiency, increasing inlet velocity also increased pressure from 70.96 Pascal in case B to 255.14 Pascal in case C, indicating stronger driving force and higher flow resistance. However, higher velocity reduced flow uniformity, with case A achieving the highest velocity uniformity index of 0.6997. This shows that case A provides the best balance between airflow strength and distribution. Okay, so for the last one is temperature behavior and solver convergence. The temperature distribution remained almost constant at approximately 300 Kelvin for all cases, with a temperature uniformity index close to 1, showing a highly uniform thermal field. The solver residuals also remain stable after initial adjustment, confirming stable pseudo-convergence. Overall, the CFD results show that higher velocity improved airflow penetration, but case A gives the most balanced ventilation performance.
In conclusion, the CFD simulation using ANSYS Fluent successfully achieved both objectives by modeling the airflow and temperature distribution in an enclosed parking lot and evaluating different ventilation configurations. The results showed that increasing inlet velocity improved by increasing airflow rate, but it reduced flow uniformity due to recirculation and bypass effects. The temperature remained nearly uniform at around 300 Kelvin because no internal heat sources were included. Overall, the study provides useful insight into airflow behavior and ventilation performance under different conditions. That's all from us. Thank you.